Hi everyone, in this video I'm going to go through the algebraic setup and the solutions for a simple version of our Solow Swan model. Now the reason why I wanted to do this video is because I was going through this model with a student and I was using the Jones and Vollrath textbook. I'll put the details of that textbook in the description below, but I realized that the algebraic calculations right at the beginning can be a little bit tricky if you're not used to it. So this video is really all about the algebra, and I'm not going to be providing any intuition or interpretation of the equations in the model. That's for another video. I'm just going to start with a production function though. So we have big Y, that's our output, is equal to some function of capital K and labor L. I'll put the list of our variables on the right hand side here, and we're going to work with a Cobb-Douglas production function in particular. So we're going to get big K to the power of alpha multiplied by big L to the power of 1 minus alpha. Now, you will notice here that there is no technology coefficient, so no big A, which you'll very often see in the Solow Swan model, and actually it's kind of a key component to the model overall. In this video though, I am really starting with the simplest case, so no technology coefficient, no A. The second thing to note is that we do have constant returns to scale, so alpha is defined to be less than 1 but greater than 0. Lastly, I should say that when we go through the proof, we will do some maths, but especially I will flag that you will need to know your rule of exponents. I have done a video on the rules of exponents. I'll link to it in the description below if you need any help with that. Right, so the first thing I'm going to do is actually put our production function in what we call intensive form. So all our variables will be per capita, so per labor or divided by L. So I'll just define some new variables here first. Let's just put down little y, which will be equal to big Y over big L. This is our output to labor ratio. I'll also define little k, which is our capital to labor ratio. That's big K over big L. I'm also going to put here that our labor will grow at some constant rate equal to n. I'm then going to just grab our production function and divide both sides by big L. So on the left hand side, I get big Y over big L, and that's equal to, well, we have big K to the power of alpha times big L to the power of 1 minus alpha, all divided by L. Now we're going to use our rules of exponents here, and so I'll start by taking that big L on the denominator and putting it up next to the rest of our variables. So we get big K to the power of alpha times big L to the power of 1 minus alpha times big L to the power of negative 1. We have two bases here which are the same, that's big L, so we can add up the exponents on them and we get big K to the power of alpha multiplied by big L to the power of negative alpha. We can then put our big L back down on the denominator and we get big K to the power of alpha divided by big L to the power of alpha. And then we can just take that alpha outside of some parentheses and we get big K over big L all to the power of alpha. Now we can use those variables that we defined before. So big K on big L is little k, so we get little k to the power of alpha. And actually here we have everything that we need to write out our production function in intensive form. So on the left-hand side, our big Y over big L, that's just our little y, and we said that was equal to little k to the power of alpha. Now, when we talk about Solow Swan, there are really two main equations in the model. The production function, which we just spoke about. The second equation is what we call our capital accumulation equation. And our capital accumulation will tell us about how our capital stock changes over time. That's going to be step 2 here. We're going to think about our capital accumulation. And actually it's pretty intuitive. So our change in capital, that's going to be notated big K dot. So dots indicate changes over time. That will be equal to S, our savings rate, times big Y minus delta times big K. So again, this video won't be much about interpretation or intuition, but just really briefly, in this model, we have a closed economy, so savings is equal to investment. I have done a video on this identification as well. I'll link to it in the description if you want more help here. But we can see because of that identification of savings with investment, the first term here on the right-hand side of the equation is just saying we have a proportion of our income of Y that we invest into more capital, and this will add to our capital stock. So we get new capital from investing part of our income. but we have to take away from that the fact that capital depreciates over time. So there'll be some depreciation rate delta that's multiplied by our level of capital. The difference between the positive effect of the new investment and the negative effect of the depreciation on our current stock of capital, that will be equal to the change in capital. So that's our capital accumulation. The next thing that we're going to do is we're going to think about an expression for the growth rate of our little k, so our capital to labor ratio. And to find this expression, we're going to take our definition of little k, so big K over L, and we're going to take logs and derivatives. Now I have done a video on this equation of taking logs and derivatives of this equation, which goes through the steps quite slowly, so I'll link to that video in the description. If I just do it kind of quickly here, well, we first start by taking the log, so we get the log of little k is equal to the log of big K minus the log of big L. We then recognize that all of these variables here are functions of time, and then we can take the derivative of all these logs then with respect to time. Now here we will actually have to use the chain rule, and what happens when we take the derivative of these logs with respect to time is that we get growth rates back. So I'll show you with the log of little k. We'll take the derivative of the log of little k with respect to little k. We get 1 over little k, and then we multiply that by the derivative of little k with respect to time. So that's d little k dt. So this derivative here is really the change in little k over time, which is little k dot. So we end up getting little k dot over little k. So we have the change in our variable over our variable. So that's the percentage change. And we're thinking about over time. So it's the growth rate in small k. So that's what happens when we take the derivatives of our logs with respect to time. We get growth rates back. So if we were to take the derivative of our log of big K and the log of big L, we're going to get the growth rates of big K. So big K dot over big K, and the growth rate of big L, so big L dot over big L back. And what we're going to do is we're going to take that equation and we'll substitute in our capital accumulation equation that we spoke about before. So if we do this, we get little k dot over k, that's our growth rate of little k, is equal to our big K dot here, that's our capital accumulation, is equal to, I'll just substitute in S times big Y minus delta times big K, that's all over big K, minus big L dot over L. Now I'll just simplify it a little bit. Let's first split up that first fraction. So we have S times big Y over big K minus, well, delta times big K over big K, and those big K's will cancel out, minus, well, big L dot over L, that's our growth rate in labor. But we said, if you remember right at the beginning, we said that in this model, the growth rate of labor would be constant and equal to little n. So I'll just put little n in. So we end up with this expression here. The growth rate of our little k is equal to S times big Y over big K minus delta minus n. The next thing I'm going to do is just multiply out that small k on the left-hand side then. And if I do that, I'm going to get little k dot, that's our change in little k, is equal to S multiplied by big Y over big K multiplied by little k minus, and then I'm going to put delta and n in brackets, and that's multiplied by little k. Now that's all equal to, let's simplify even more. And what I'm going to do with this first term is just multiply and divide by 1 over big L. And this will put our capital and our output in terms of their per capita variables. So I'll just put L here, that's labor, under Y. So I've multiplied that numerator by 1 over L. And I'm also going to do that to the denominator, so I'll put L under K. Now, this action hasn't changed the value of the term because I've essentially just multiplied the numerator and the denominator by the same term, but it will make it clear that we can rewrite this now as S times, well, little y over little k, all multiplied by little k, and those little k's then will cancel out. So I can rewrite the whole equation then as S times little y minus delta plus n times little k. Now, one last step for this part. From way back at the beginning, from our production function in intensive form, our little y is equal to little k to the power of alpha. So I can substitute that in, and I get little k dot is equal to s times little k to the power of alpha minus delta plus n multiplied by little k. And now we have our capital accumulation in intensive form, so all of our variables are per capita. All right, so the next step is to solve for this simple model, and in the steady state, which is our equilibrium outcome in this model, the change in the capital to labor ratio is equal to 0. So little k dot is equal to 0. And well, what does this imply using our equations then? Well, this implies that using our equation here for little k dot, we get s times little k to the power of alpha minus delta plus n multiplied by little k. That's all equal to 0. And now what I can do is just solve for little k, and this will be our steady state equilibrium little k. And I can start by just moving a bunch of stuff to the left hand side. So we're going to get s times little k to the power of alpha is equal to delta plus n all times little k. And then I can divide both sides by little k, and it cancels out on that right hand side. I can then put our little k that's on the denominator here on the left hand side up the top. So I'll get s times little k to the power of alpha times little k to the power of -1. And that's all equal to delta plus n. I'm going to neaten up that left hand side. So I'll get s times little k to the power of alpha -1 is equal to delta plus n. I can then divide out that s, and I get little k to the power of alpha -1 is equal to delta plus n divided by s. Now I do need to get rid of that exponent on our little k, so I'm going to raise both sides of the equation to 1 over alpha -1. This will cancel out the exponent on the left hand side, so we're left with little k is equal to delta plus n over s all to the power of 1 divided by alpha -1. Now this is a perfectly fine expression for our steady state level of capital per labor. The problem is though that this exponent will actually turn out to be negative, and the reason why I can tell that is because alpha is less than 1. We said that right at the beginning. So alpha -1, that's our denominator, will give us a negative number, and so the whole exponent will turn out negative. And that means that it's actually just pretty hard to interpret what's going on in our expression here. So how s or delta or n affects our little k. If we use our exponent rules to our benefit though, I can swap the place of the numerator and our denominator in my equation, and that will mean that I can introduce a negative sign to our exponent, which will turn it back positive. So that's what I'm going to do. So I get the final expression for little k star, that's our steady state capital per person, is equal to s over delta plus n. So we just swapped the place of the numerator and denominator, but I have to introduce a negative to our exponent, and I'll get 1 over. So I'll leave the numerator as is and just introduce the negative at the bottom. So 1 will now be positive, and then minus, so alpha is now negative, and that's our steady state value of little k. Right, good. And this over here, given that alpha will be less than 1, the exponent will be positive, and it's easier to interpret how our savings rate, how our depreciation rate, and our n, how it affects our steady state capital to labor ratio, little k star. Now there is one last thing to do, which is just to solve for our steady state output per capita, which is little y star. Now from the beginning again, little y star is equal to little k to the power of alpha. In order to find the steady state value, we'll just use little k star, which is all equal to the expression we just found. So I'll substitute it in. So I get s over delta plus n all to the power of 1 divided by 1 minus alpha, which is all to the power of alpha. We can consolidate this and get rid of those outside brackets, and we get s over delta plus n to the power of alpha divided by 1 minus alpha. So that's our steady state output per capita, and that's really the algebra that goes into our simple version of our Solow Swan model, so with no technology coefficient. In the more complex versions where you do have technology, if you're not up to it yet, you'll see why, but actually technology is very important for this model. But in those versions, you're going to be using the same sort of algebra that I showed you in this video. So hopefully it helps you there as well. But thank you so much for watching this video. I do hope that it helped. If it did, please like and subscribe. Have a good one, everyone.